Alright, let's continue our discussion on thermodynamics. Basically, what we're going to do this time is we're going to introduce you to some concepts of work and also define the first law of thermodynamics. Basically, I'm going to perform an energy balance using these different types of energies that we've discussed. So what's work? So remember we talked about heat crossing in and out of the boundaries. We talked about something that's adiabatic. Well, with work can also cross the system, but work does not depend on a temperature difference. Work, what we're going to consider as work, is basically a force acting through a distance. Now that includes a rising piston, rotating shaft, can have electrical work, all different types of work crossing the system boundary. Now there are a lot of different sign conventions, I think, depending on the text that you're using. For example, in this text they use subscripts of in and out to do our energy balance. What I'm going to use, and that's because the way I learned it, I'm going to use in our examples when heat is transferred to a system and when work is coming out of a system, we're going to consider that positive. When heat is transferred away from a system or work is put into a system, we're going to call that negative. Alright? And we'll practice those as we go along here. Work has the same units as heat transfer. We're either going to be using kilojoules if we're expressing in terms of energy, or if we want it per unit time, we'll be talking about watts or kilowatts. Now, what is the difference between heat and work? Well, remember, heat depends on a temperature difference. Both are acting on the system boundaries, so they can cross the system boundaries. Even in a closed system where mass is constant, we can have both heat and work cross that boundary. Now, one thing you may note is the convention, the sign convention in your textbook. And it's an important distinction. So, with pressure, temperature, volume, internal energy, enthalpy, these different types of parameters, these are all going to be point functions. So we're going to take those functions at a particular point at a particular condition. So here at point 1, we know the pressure and we know the volume of that system under that condition. So those are point functions, and we express those in terms of a differential, using an exact differential. For those of you who've had calculus, you're familiar with this. The differential is expressed by using a lowercase d. For work and heat, you're going to see we use a squiggly line instead of a lowercase d. This is a delta, the Greek letter delta. Well, the reason we use that is because it's dependent on the path, not the point. So if we know the conditions and we know what the system is like at point 1, and then it comes to equilibrium, we know what the system is like at point 2, we can treat that as a point function. Well, the path that process has taken is going to be where work and heat have been transferred to or from that system. And to denote that, we use a different sign convention. So we have an inexact differential to denote work and heat. One type of work is electrical work. So if we have a resistive heating element in our system, we can calculate how much work is done in that system by multiplying voltage times current. Now the units of voltage times current are in watts. Now, and if we take it and we multiply it by the change in time for how long we had that in our system, we will have the amount of energy transferred to that system. So depending on how you want to express that, you can show it in a couple different ways. Now, another type of work, and the ones that we'll be talking about a lot, is we're going to be talking about a force that moves a certain distance. So the force must be acting on the boundary, and the boundary must move when we're talking about this type of work. You see Dagwood laying down there? He's not working. He's not moving. He's not exerting a force. So one example of that is shaft work. So shaft work is when we have energy transfer from one, here in this case we have transfer of energy from an engine to a propeller that drives the and provides propulsion for this boat. You guys may also experience this in your automobile, where we have energy transfer from your engine to a shaft that drives the tires. From a pump, so we may have some type of motor or engine that drives a pump and uses a shaft to transfer that energy from one location to another. The way we express that mathematically is we will have 2 times pi times the number of revolutions times the torque. That would give us how much work is exerted in kilojoules from our shaft. If we wanted in kilowatts, we would take the revolutions per second or revolutions per minute and convert the units accordingly. We may also deal with some spring work, where we have a spring constant times the amount that the spring was displaced. That would give us amount of force exerted to move that spring. The work is going to be the amount of force at times that displacement. So you see here substituting and integrating. Here in this example shows that the work done by the spring is 1/2 times the spring constant times the location it is at the second position squared minus the first position squared. So that's another way we could use to calculate the amount of work done by a spring. Now, we can add up all of these different types of energies. So we have, recall, the energies associated with our system, which is internal, kinetic, and potential. And we have the energies associated that cross the boundaries. So we have heat and work. Now, if we add up all of these, both inside and outside, or the things that are crossing the boundary, we have the first law of thermodynamics. It's basically an energy balance. So we have energy into the system minus energy out of the system equals a change of energy inside that system. In other words, energy can be neither created or destroyed during a process. It only changes forms. And I hope you leave this class knowing this principle and hopefully seeing how it applies to many different types of cases in engineering. We see a nice example here. Potential energy of a boulder being converted into kinetic energy. Still, if it's moving, it's still, the addition is 10 kilojoules. Cannot lose energy, cannot add energy to the system. We can only change forms. So here's an example. Remember I said energy in minus energy out equals a change in energy in the system. Well, here we have in the top left corner we have a pot. We're adding 15 kilojoules of energy to our system. 3 kilojoules of energy are leaving our system. And what's been collected inside by the water being heated here is a total of 12 kilojoules. So all the energy is accounted for by the different properties here. We have a few other examples. We have work being added to our system, and that would result in an increase in energy in that particular system in both these other cases. So here's what I mentioned, just shown graphically. We have the total energy entering minus the total energy leaving equals the change in energy in the system. And I really like the example on the bottom right here on 345. So we have work from the shaft into the system we have heat transfer. Maybe we have like some type of candle. We have some type of heater putting energy into the system. So we have 15 plus 6. We have 21 kilojoules being added into the system. 3 kilojoules leave the system. So that would give a total of 18 kilojoules that need to be accumulated into this system in order to satisfy the first law. So what we're going to do is we're going to look at the energy in the system at the final state, and we're going to compare it to the energy at the initial state. So remember, when we're looking at that right side of the equation, we're always going to compare it to a particular reference state. So we're going to take all of our kinetic, potential, and internal energies, and we're going to compare it to a particular state. So here you see how we're going to define that. Mass, since it's big U, it's mass times little u minus U1. And the other kinetic and potentials are expressed similarly. So here we're just talking about different ways that heat can be transferred. I'm not going to talk about this slide too much. I really want to focus on closed systems first, but I'll mention this. This is an open system where we have a control volume, and we also have some mass flow rate through the system, which is also contributing some work. We will talk about that in more detail in a later slide. But for now, just be familiar that we can have energy transfer through heat, work, and we can have heat transfer also through some flow work that can be done in the system. And we'll discuss that at a later time. An important parameter that you guys will see a lot and is very practical, it's used in many applications, is efficiency. How efficient is it? And typically, it's hard to think of an application where you wouldn't want it to be as efficient as possible, specifically when you're dealing with some type of energy transfer. So if you're talking about a water heater in your house, you want it to be really efficient because you don't want to spend as much money. So how we're going to define energy is how much this system outputs versus how much the system is needed as far as an input. So how much fuel do you need to apply to this water heater in order to get a certain temperature of water? And that is going to be dictated by this efficiency. Now, usually the higher the efficiency of the object, the more expensive. Not always the case, but since you're saving money, you can do a balance and you can do a check to see if the investment is worth the amount of savings you'll get. But efficiency is just a really quick guide to know how you perform relative to others for a particular unit. And there are limits to how efficient something can be. We'll talk about those limits too. Now here is an example of combustion efficiency. Alright, so if we have that gas heater, let's say this is some type of natural gas powered water heater. Well, the amount of heat that water experiences while rising, or the amount of heat that's released due to combustion, divided by the heating value of that fuel. And this is kind of a side note, but you guys can use this. You can apply this to gasoline in our car engines. We can apply this to many different applications. But heating value can be expressed in different terms, but basically it's how much energy is concentrated in a particular fuel per unit mass. And there's different forms: lower heating value, higher heating value. You don't need to concern yourself with that. But you can know that a particular fuel has a particular amount of energy associated with it. Combustion is something that is a part of thermodynamics, and you'll be taking that in the next section of this class. But we will not discuss that. But for purposes of illustration, we can talk about how efficient the combustion of something is. We can talk about the overall efficiency of a system too. If we consider combustion efficiency times a thermal efficiency times something that maybe if we're talking about a generator, we can basically look at the overall efficiency of something. Now, having a higher efficiency means you spend less money. It also means that you consume less energy, which results in less pollutant emissions and may help the environment. So it's good in many ways to use energy efficient devices, but at some point the cost may become limiting for their use. So there's a balance. But if possible, and things are increasingly becoming more efficient homes, more efficient air conditioners, which means that the energy they consume, they're better able to deliver to whatever application they're interested in. So there's many different types of efficiencies that we're going to be talking about throughout the class. But just like we described a few slides ago, in general, we're going to be talking about the mechanical energy output over the mechanical energy input. So if we have a fan and we deliver 50 kilowatts of energy to the fan, and only 70% of the energy is transferred to that liquid or that fluid to help it move through the system, that would be in a 74% efficient machine. And we can have a similar measurement of efficiency for a turbine if we had flow passing from one side of this pipe to the other, and we were able to extract 74% of the energy that's associated in that fluid. That turbine then would be 74% efficient. And we can use this in various applications. I'm just going to show this slide here. I'm not going to go through the different types of efficiencies that carefully. You can use your book. But really, I feel like when you'll make the connection to this is when we start working out problems and we start making connections between how efficient something is and when something requires power and the output. But in general, we're going to be talking about two types of devices, turbines and pumps. Pumps will always output less energy than they consume, and we can expect the opposite from a turbine. A turbine will always output less energy than was put in or that it gathered from some energy device. Okay, so keep that in mind. Keep these facts in mind. So I've introduced to you guys the first law of thermodynamics now. The next logical step is to work out some problems in this area. Make sure that we understand the application of the first law, how we are doing an energy balance. Energy in minus energy out equals the change in energy in our system. We talked about different types of energy. And this is going to be a central concept for many of the other topics we talk about in this class, also relating even into fluid mechanics. So keep that in mind as we progress in here, how many applications a conservation of energy has.